Okay, we're in section 5.1, a brand new chapter, and here we're talking about higher order polynomial functions. That's a big phrase. We're going to unpack all of that. And we're going to look at an analogy to the awesome 1984 movie Break-In, but that'll be in a minute. Before we do anything, I want you to look at this graph of this function. On the horizontal axis, we have years since 1980, and on the vertical axis, we have per capita consumption of breakfast cereal. So like in 1982, breakfast cereal consumption was, it looks like just under 12 pounds. So per person, in 1982, people were eating 12 pounds of Cheerios or whatever breakfast cereal they were eating. And this is kind of how the graph looks. So the question I want to ask you is this graph concave up or concave down? So we know concave up is sort of this general shape and concave down is this, this general shape. And this one's a tough one. You know, if I say concave down, I'm sort of ignoring some stuff that's going on over here. And if I say concave up, I'm definitely ignoring some things that are going on over here. So the answer to this question is actually both. It's both concave up and concave down. So for this first section of the graph, we would say that is concave up, and then at a certain point it changes and becomes concave down, and then actually goes concave up again. We've seen a smattering of examples where concavity changes, and we know that there's a point wherever the concavity changes that's called the inflection point. But so far in the functions that we've seen, linear functions and quadratic functions that we've really done a deep dive in, neither of those, well, linear functions don't have concavity, and quadratic functions only have one type of concavity, and so that concavity never changes. And this particular graph looks like it has, well, how many concavities would you say it has? We would definitely see this one right here. That's one concave up, and then maybe about right here, we've got this where it's going concave down, and then looks like it's trying to go concave up again. So I would say that this function has 3 concavities, up, down, and then up again. So from 0 to about, on the x-axis, maybe about 8, we're seeing that it's concave up. And then from x equals 8 to, let's see, about somewhere around 17, it's concave down. And then from 17 to 20, we would say it looks like it's tending towards concave up again. So remember, this is our interval notation. A square bracket indicates that you're including the endpoint, and we'll kind of include this too, I guess. Let's fix that. Yeah, not like that. And a round bracket means that you're not including the endpoint. And I'll include these endpoints here. This guy I'm not going to include at 8 because he's a point of inflection, so it's neither concave up or concave down, so that's why I used a round bracket. Same story here. At this point, it's a point of inflection. Another point of inflection at 17, it's neither concave up or concave down, but my endpoint 20, I'll say that it's still tending towards concave up at that point. So I'll include these endpoints, and I'll indicate each of these transition points, these points of inflection, but they're not going to be included in the description of being concave up. So with linear functions, we had these literally straight lines, and so there were no concavities in those types of functions. With quadratics, all that we were talking about in chapter 4, it was either concave up or concave down. It never switched. It was always just one or the other. And so for quadratic functions, they only have one type of concavity. It's either concave up always or concave down always. And so now we're going to start diving into functions where we get multiple concavities, and we get maybe 2, 3, 4, and on, different types of concavities. And this is the idea of a higher order polynomial. A linear function has no higher powers than 1. A quadratic function has no higher powers than 2 on the variable. We're going to start looking at functions where the highest power is 3, or the highest power is 4, or maybe that highest power on x is 5. And so when I think of these shapes, it reminded me of this movie I watched religiously with my siblings as a kid, Break-In, where, among other things, there was this one dance move called the wave that you could do with your hands, and you would like move them. People still do it, I'm sure, but this is basically the types of functions that we're going to start looking at. So think of the wave, and these functions are going to have a lot of different concavities. After quadratic functions, next in order come cubic functions, and they generally look like this: y equals ax cubed plus, then you could have a squared term, a linear term, and a constant term, but you always have this cubed term in a cubic equation. After cubics come quartics, and they look like y equals ax to the 4th plus, and you can add cubic terms, squared terms, linear terms, but it always has to have that 4th power. And then you could have a quintic equation, which is y equals ax to the 5th plus a bunch of stuff. You can keep going and going and going, always just having higher orders to these polynomials. So let's start our discussion by looking at the most basic type of cubic function, y equals x cubed. And I haven't graphed it yet, but remember when we were looking at y equals x squared, it was this really basic parabola that went through 0, 0 like this. And think for a minute what y equals x cubed might look like. Think about numbers over here. If you cube 1, that's 1. If you cube 2, whoa, that shoots up pretty fast. That's 8. 2 cubed is 8, and 3 cubed is 27. So it's shooting up fast. What's happening over here with negative numbers? Are they shooting up like that? Let's think about what is negative 2 cubed. So negative 2 cubed would be negative 2 times negative 2 times negative 2, which is negative 8. Oh, okay, so this actually shoots down, and it shoots down pretty quickly. So when we graph this, it's going to look like this. And we can see things, ways that it's different already from a quadratic equation, those parabolas. First of all, it's concave down for the first half of its little journey across the horizontal axis, and then it turns concave up. It does go through the point 0, 0, so it has 2 different concavities, and it has 1 inflection point. So if this right here is the most basic type of cubic function, this right here is probably a more typical cubic function because we have more terms that were allowed in a cubic function. A cubic function, the only rule is the highest power on x is 3. And then for any polynomial function, what you've got is you've got these powers on x can be any integer. You know, technically 0 is the power on x right here, 1 is the power on x right here, 2 is the power on x here, 3 is the power on x here, and you can have coefficients be anything. This could be 5, it could be 7.3, it could be anything, but a polynomial is just this string of terms that you're adding or subtracting together, and the important thing of the term is it has a coefficient, and then it has your variable to some integral power, so some integer power. And the highest power on your polynomial is called the degree of the polynomial. Okay, but we're getting a little ahead of ourselves. Let's just focus on graphing this and what we think this cubic function will look like. So let's take this guy off, and we'll put this guy on. This is a cubic function too. So this cubic function, how many concavities does it have? Let's see, as we go like this, it's definitely concave down. And then right about here, it switches and becomes concave up. So this right here is our point of inflection. Point of inflection is at 0, 1. We have a relative max right here. At this point, negative 0.4, 1.96. It's not the absolute maximum because later on the function actually does achieve higher y values. But relative to its neighbors, this guy is a relative max. And I bet you can see a relative min right here. So it's not the absolute minimum of the function because later on or earlier on the function goes even lower than this negative 1.074. let's see, what else have we got going on here? Why does Desmos give us these 3 points? These are our 3 horizontal intercepts. So Desmos is so awesome, it'll find those for us. So it's given us a lot of information. It's given us the inflection point, it's given us these horizontal intercepts, and the relative min and the relative max. So just like the first one, y equals x cubed, we're seeing 2 concavities and 1 inflection point. This also is a cubic function here. And remember, the only rule to be a cubic function is your highest power in x is 3. It doesn't have to have these other terms, like this one doesn't even have an x squared term or a constant term. That's fine. As long as you've got your x cubed term, it's a cubic function. And here we have a coefficient that's 1.2. No problem. Your coefficients can be any real numbers. And for the first time, our leading coefficient is a negative number. How do you think this function here will look compared to this one up above? So let's graph both of them at the same time. Okay, so this is interesting. When we start with a negative coefficient, as we go off to, as x gets bigger and bigger, actually y gets smaller and smaller. It goes off to negative infinity. So that is an indication of when you have a negative lead coefficient, that will happen in a cubic function. That as your x's get bigger and bigger and bigger, your y values get more and more and more negative. So let's compare these again. Here we had a positive leading coefficient, that 5, and as our x values got bigger and bigger and bigger, the y values got bigger and bigger and bigger also. Okay, let's go back to this guy. We still have 2 concavities. Here it's concave up, then we have this point of inflection right here, happens to be at 0, 0, and then we go concave down. So it's looking like, in a general way for these cubic functions here, anytime we've had a cubic function, we have 2 concavities, 1 inflection point. And then this lead coefficient kind of tells us what happens as x gets really big or as x gets really negative. This lead coefficient will determine what the y values are doing. I want to look for a minute at exactly what numbers Desmos is giving us. It will always give you like the local, this is called a local extreme, a local max and a local min right here. So here they are. And if you see the phrase local extrema, it's always just talking about that whole collection of local maximums and local minimums. Desmos is also giving us all of the times that the graph hits the horizontal axis. So these are the x-intercepts, or the horizontal intercepts of the graph. So this particular cubic function hits the x-axis 3 times. And lastly, it's going to give us the y-intercept where it hits the y-axis. So it gives us that y-intercept. Unfortunately, and I may have misspoken before, the Desmos does not give us inflection points as sort of default points. In this particular function, the point of inflection actually happens right around here. And you're not expected to know exactly where it happens, but just roughly. I happen to know exactly where it happens, but Desmos doesn't give this to us. But you should be able to eyeball kind of where an estimate of the point of inflection will be. So I want to summarize some of the things we learned by looking at those graphs of cubic functions. First of all, this is standard form for a cubic function. You've got your leading x cubed term, and then all the other guys just follow along. You have an x squared term, an x term. Whoa, I have too many here. I definitely don't need that. I already have a constant term. Okay, so this is what a cubic function should look like. So the name of this type of function is cubic. Do you remember what the degree of any polynomial function is? It's always the highest power on the variable. So the degree of this function will be 3. So let's try to figure out the rest of these other 3 characteristics here. The number of concavities in a cubic function, that is going to be, let's see, we saw that each of those had 2 different concavities. There was a part where it was concave up and a part that it was concave down. Number of inflection points, each of those cubic functions had 1 inflection point. And then the end behavior of the function, what's going on as x gets really big or as x gets really, big negatively. As we're going off to the right and to the left of our graph, one end is always going to go to infinity. So one end is going off to infinity, and one end will go off to negative infinity. Negative infinity. And these functions generally look something like this. It might be reversed, or maybe one end, the other end is going up when the other end is going down, but this is the general shape of a cubic function. Let's think about a quartic function now. Highest power is 4, so this is the most basic type of quartic function. And before I graph it, I want you to think, can this function ever take on a negative value? In other words, any input you put in, could you ever pop out a negative value? And the answer is no. Any number you input into this, it'll always come out as a positive number. So we get this sort of, it almost looks like a parabola. It's not quite a parabola because it's a little bit too flat in here. But this is the most basic type of quartic function here. Things do get a little more interesting with quartic functions, so let's look at another one. So here I've got a quartic function where all the terms are represented. I have a x cubed term, an x squared term, an x term, and a constant term. And we know what this one guy looked like, so let's see what this other quartic equation looks like. Okay, so this definitely is more interesting than the first one, and we're seeing a few different things. We see concave up right here, and then it turns concave down, and then concave up again. So we actually have 3 different concavities here, and that'll mean we've got an inflection point about right here, and an inflection point about right here. With a quartic function, you're either always going up, your end behavior as x gets larger and larger, on the x-axis, you're always going either up, both ends are going up to positive infinity, or both ends are going to go down to negative infinity. So this was the most basic type here. In this green graph and this red graph, both ends are going up to positive infinity. Let's see if we can make one where both ends are going to negative infinity. So if we want to make a quartic equation where both ends are going to negative infinity, my guess is that it has to do with this lead coefficient. So I'm going to make a negative 3x to the 4th. And yeah, so both ends got off to negative infinity. I'm going to add a little bit more just to make it more interesting. So this is a quartic function. Let's take a look at how many concavities are here. So as we're traveling up here, looks concave down, and then it switches to concave up, and then right about here, concave down again. So we're seeing 3 concavities in this quartic function. So with quartic functions, you're either going to have 2 concavities, both of these you're either going to have 3 concavities, both the red and the blue ones had 3 concavities, or you might just have 1 concavity. This is standard form for a quartic equation, for a quartic polynomial function. And these are both examples of how that quartic could have looked here. With the quartic function, we're getting, well, the degree is 4, that's the highest power on the polynomial. We're either getting 1 concavity or 3 concavities. And so we either have 0 points of inflection or we have 2 points of inflection. And the end behavior, both ends go to either positive infinity or negative infinity. So right now I want to make a little room because I want to put the functions that we've already learned about up here and compare them. We've learned about linear function and quadratic functions. So linear functions, they always look like these straight lines. And quadratic functions are some sort of parabola. Linear functions have degree 1. There are no concavities, no inflection points, and the end behavior as one end goes to infinity and the other end will go to negative infinity. And then a quadratic function, the degree is 2, that's the highest power on a variable. It has 1 concavity, no inflection points, and its end behavior is both ends will either go to positive infinity or negative infinity. So both ends go to positive infinity or negative infinity. We've got all of these different characteristics of functions that we've talked about. Remember this guy, our library of functions? We, at the very beginning of the course, we said we were going to talk about 6 major types of functions. And we spent a lot of time on linear functions. We've spent all of chapter 4 on quadratic functions. And here today we're seeing higher order polynomial functions, these cubic, quartic, and in a minute we're going to talk about quintic functions and how they behave. So we're really, traipsing our way through these different types of functions. I want to briefly touch on quintic functions, and here we have the most basic type of quintic function, and here we have a pretty elaborate quintic function, and we'll compare them. And this will be the last higher order polynomial function we look at, but it will continue the pattern of what we've seen already. Okay, let's take a look at y equals x to the 5th. First of all, the one thing I want you to guess is what will the end behavior of this function look like? Will both ends go to the same infinity, or will one end go off to positive infinity and one end go off to negative infinity? So maybe this is what you guessed. Hopefully it is. Yeah, these odd powers seem to be going, their ends seem to be going in opposite directions, and that's certainly true. We can definitely get some negative y values from a quintic function. Okay, let's take a look at this other guy and see how he compares. Whoa, okay, so this quintic function has a lot going on. Let's take this off for a minute. We have, as we come in here, we're concave up, and then just for a brief moment, we actually go concave down right in here. And then we're back concave up, so already we're at 3 concavities, and then concave down. So this quintic function has 4 concavities. That means it's going to need 3 inflection points, and its end behavior is what we expected. One end is going off to negative or positive infinity, and one end is going off to negative infinity. So with quintic functions, we saw the degree was 5. I didn't bother to write it all out, but it follows the same pattern. You're just going to have a 5th degree x term. There are either 2 or 4 concavities. It could have either one, and that means there's either going to be 1 or 3 inflection points. And with this 5th degree polynomial, one end is going to shoot off to positive infinity and one end is going to shoot off to negative infinity. So this is a good chart of all these higher order polynomials. Well, these guys are higher order polynomials here, but the ones that we've seen, linear, quadratic, and then today we talked about cubic, quartic, and quintic, and just kind of how they compare and how they look and in their end behavior. And we talked about what the term degree means, and importantly, their concavities and inflection points. The last thing we need to talk about is the idea of regression with these higher order polynomials. Just as we were able to do linear regression and quadratic regression, sometimes we'll get data that looks cubic, or maybe there's like tons of different concavities and we need a quartic or a quintic function to model the data that we have. So let's take a look at regression with some of these higher order polynomials. So regression with these higher order polynomials comes about because sometimes we have data that looks cubic or maybe quartic. It doesn't look linear, definitely doesn't look quadratic, but maybe follows the pattern of one of these polynomials, and we'll need that type of regression. Okay, here's the example that we're given. We have projected internet usage in hours per person per year, and this is going, looks like from 1995 to 9 years later, so to 2004. So in 1995, it was estimated that the average person used 5 hours of internet per year. That's hilarious. And then the numbers obviously go up and up and up and are quite a bit right now. So our first job is find a good regression model for the above data. Okay, so this regression model might be linear, quadratic, cubic, quartic. We don't know yet, but let's go ahead and plot this data using Desmos, and we'll get a look at kind of what it looks like, and that'll give us a good feel for what regression we want to use. I've gone ahead and entered all of the data in a table, and I'm going to plot this data here. And I'm going to use this little guy down here, this magnifying glass plus, to give me a good screen, a good view of the data. Okay, so here's the data. I could try different things. It could be a linear regression. It doesn't really look quadratic to me, but I'm noticing that here at the beginning it's sort of concave up, and then at one point it switches to concave down more. So since we know what it is now, I'm going to try a cubic regression and see how close that regression will come to the actual data. To do any regression, I always start off with y1 and then this tilde, and then I need to give it a model for how I want Desmos to do the regression. Do I want it to give it a linear model, a quadratic model, cubic, quartic? And this time I'm going to give it a cubic model. So I'm not done yet, but I start off by telling it ax1 cubed, and you'll use this button to get that cubed. You'll have to say x and then this button, and then you'll enter 3 to indicate that you want a third power. So I've finished entering everything in. I've given it a full cubic function to work with, and what it spit out was this as a regression, and it's given me a really good R-squared. This means it's a good fit for the data. These are my parameters here. A equals this number, B equals this number, C equals this number, and D equals this number. So I have my model. So at this point I'll take all of the information Desmos has given me and create my regression model. And so here it is. Here's my regression model. I can input any year, and this model will estimate the number of hours the typical person uses per year on the internet. And the R-squared was so good, so I can say that I've done the first thing that they asked me to do. The second thing they asked me to do is use our model to estimate internet usage in 2007. So this would be when t equals 12. I have a couple different options here. I can just input 12 into here and, calculate what this whole big old honkin' thing would be. I'm going to be a little bit quicker by just using the graph, and I'll show you how to do that. So essentially, to find out what's going on in 2007, I want to know when t equals 12, what is this graph doing? And Desmos likes x's and y's, so we'll actually say when x equals 12, what's happening. When our input value is 12, not that, how about this? When x equals 12, what is the function doing? And we'll just look at where they intercept. And it says that the function is 177.915. So using the model, I found out that in 2007, the model predicts people will be using the internet 177.915 hours, and that's per person per year. This is a terrible estimate because realistically, internet usage is not going to go down. It's going to keep going up. So in a situation like this, where I know that realistically this is not a great estimate, what I would do is go back and get more data. So we've definitely answered their question, but really, we should collect more data. So the big ideas from today were these higher order polynomials, and we talked a lot about their different characteristics, their different concavities, how many inflection points they would have, and their end behavior. We also talked about the term the degree of a polynomial, that it's the highest power on a variable in a polynomial, and we now know how to do a lot more regressions. We can do cubic, quartic. Because we now know the forms of these higher order polynomials, we can tell Desmos how to perform these higher order regressions if our data seems to look like it, maybe if it has a lot more concavities.